So this is Introduction to Matrices. It is the beginning of Stacy Rodman's chapter 3 of her linear algebra text. So first of all, what is a matrix? Definition. A matrix is a rectangular array of numbers written as such with m rows and n columns. So for example, the entry A sub 2, 1 is the entry in the second row in the first column. What can we do with a matrix? Well, here are some basic operations that we can use. So the sum of two matrices. The sum of A and B can be only done when the number of rows and columns of A and B are the same. It is defined as such. So it is easier to follow an example than to look at this definition. It's pretty simple. You just take the same entries in each matrix and add them together. So for example, A11 and B11, you would add them together. So 3 plus 7 would give you the entry in the top left of the output matrix. Now the scalar product definition. The scalar product of T and R and A is defined by this as such. So T is a real number being multiplied by a matrix. And what you do is you can kind of think of it as distribution. So like the scalar 2 times that matrix 2, 4, 6, 8, the 2 gets distributed to all of the entries in the matrix, and the output would be 4, 8, 12, 16. Now the product of two matrices. The scalar product of A and B can only be done when the number of columns in the left matrix is the same number of rows in the right matrix. It is defined as such. Now this definition can be a little confusing, so we'll walk through an example. So so what we're going to do is we're going to go across the row of the left column or of the left matrix and down the column of the right matrix. So we'll start out by 3 times 5, and then plus, and then we'll go over in the row to 4, and then down the column to 1. So 4 times 1 plus 1 times 2, and that'll give us our entry for the top left entry in the output matrix. And then the resulting matrix will be it'll be the dimension, it'll be the number of rows in the first column and the first matrix, and it'll have the number of columns in the second matrix. That's why it's a 2 by 2 matrix at the end. So back here, now we're going to look at special types of matrices. So we have the additive identity. So an additive identity for the set of n by n matrices is an n by n matrix 0, such that for all n by n matrices, m plus 0 equals m. 0 is also called the zero matrix. Now, an example. The additive identity for an arbitrary 3 by 3 matrix is as such, because when you add this to any 3 by 3 matrix, you'll just get that 3 by 3 matrix. And you proved that this is the additive identity and that it is unique, but that is not what we'll be focusing on. Now, the multiplicative identity. A multiplicative identity for the set of n by n matrices is an n by n matrix I, such that for all n by n matrices m times I equals m, and I times m equals m. So example, the multiplicative identity for an arbitrary 3 by 3 matrix is as such, because when multiplying any arbitrary matrix by this, you will then just get that arbitrary matrix again. So now moving on to the determinant. The determinant is a useful process for assigning a real number called the determinant to any square matrix. For n by n matrix A, this number is written det A, or it looks like the absolute value A. Now, the determinant for a 2 by 2 matrix A can be defined as such. So A, B, C, D, that's going to equal the real number A times D minus B times C. So you multiply the two entries in the top left and the bottom right, and then subtract the two entries, B in the top right and the bottom left. Now, cofactor expansion. So this is our way of solving for the determinant by breaking a matrix down into the sum of 2 by 2 matrices determinants. So this is how we can take the determinant of any sized matrix. So given this 3 by 3 matrix, this is how we're going to do it. So we're going to start in the top left with A. That's going to be our coefficient there. And then we will have, we'll cover the row and the column that A is in, and that'll leave us with the matrix EFHI. So it'll be A times the determinant of EFHI. So now we subtract, because we go plus, minus, and so on when we do cofactor expansion. So now we have B, so minus B, and then we cover the row and column B is in, and that leaves us with the matrix DFGI. So minus B times the determinant DFGI, and so on. You do the same thing with C, and then you can simplify that using the definition of how to solve for the determinant of a 2 by 2 matrix to get this. Now moving on to elementary matrices. So definition, an elementary matrix is a matrix that when multiplied on the left of a given matrix performs one of the 3 elementary row operations for reducing a matrix. It can 1. Rearrange the order of the rows, 2. Multiply a row by a non-zero number, or 3. Add a multiple of one row to another row. So examples of these 3 types. 1. Switch rows 2 and 3. So this is pretty much just the multiplicative identity, except the multiplicative identities rows 2 and 3 are switched. Now, if you don't trust me on this, you can take any arbitrary matrix, multiply this matrix on the left of it, and you will then have switched rows 2 and 3. That's just the way that our matrix multiplication works. So now 2, multiply row 1 by 4. It's our multiplicative identity, but in the first row, that 1 is changed to a 4. That'll multiply everything in the first row of an arbitrary matrix by 4. And then 3, add 3 times row 3 to row 1. You put a 3 in the third column of the first row of the multiplicative identity, and that will do that for you. But notice, the determinants of the 3 different types of elementary matrices that we created are non-zero. This holds true for all elementary matrices, but this is not a proof. It is just evidence. You could prove, though, that the determinant of an arbitrary elementary matrix is going to be non-zero, but for now, it's just important that you know that that is true because it will come up later. Feel free to prove this if you want to. So that's just like a bunch of different information that you needed to know about matrices. And now we're going to see how it all works together. So putting it all together, we can use this to solve some theorems now, or prove some theorems. So first, the elementary matrix lemma. For any n by n matrix M and any n by n elementary matrix E, we need to show the determinant of E times the determinant of M equals the determinant of EM. So we must show this for all 3 types of elementary matrices. However, the idea can be demonstrated by showing one of the ways. We don't know, we could show all of the ways, but it's pretty similar. So we're going to do an informal proof of part 1, where E is our example of an elementary matrix that rearranges the orders of the row. And if you want to, you could solve the other 2 ways. Now, so let E equal that elementary matrix that switches rows 2 and 3. Let M be the arbitrary matrix A, B, C, D, E, F, G, H, I. And then that means that EM is going to be A, B, C, G, H, I, D, E, F, because rows 2 and 3 were switched. Now we know determinant of E equals -1 because we already solved for it in a previous slide. And by cofactor expansion, we'll get that determinant of M is this, A times EI minus FH minus B times the quantity DI minus FG plus C times the quantity DH minus EG. Now determinant of E times determinant of M equals -1 times all of that. So then it'll just be, it'll just make that whole thing negative. And recall that EM is A, B, C, G, H, I, D, E, F. And by cofactor expansion, the determinant of that is going to equal the same thing as the determinant of E times the determinant of M. Therefore, determinant V times determinant of M equals determinant of EM. So we showed what we wanted to, and the other two cases are very similar, where you have the other two types of elementary row operations, or the other two types of elementary matrices. So we are just going to let you do that. Now we're going to use the elementary matrix lemma as a big tool to solve theorem 25. This is going to be our big theorem in this, this video. So theorem 25, for any two n by n matrices A and B, we must show determinant of A times determinant of B equals determinant of A times B. Now there are two cases. Either A row reduces to the multiplicative identity, or it doesn't. So if we can show that determinant of A times determinant of B equals determinant of AB in both cases, then we've proved it. So first, let's assume that it does row reduce to the multiplicative identity. So assume that some string of elementary matrices times A will get down to the multiplicative identity. That's what being row reduced to the multiplicative identity means. Well, if that were true, that would imply that you can break them up into the different determinants. So determinant of E sub n, determinant of E sub 2, and so on, determinant of A equals determinant of I. We can do that by the elementary matrix lemma. And then we can, because the determinant is a real number, we can divide over the determinant of the elementary matrices onto the other side of the equation to get determinant of A equals 1 over the determinants of all of the elementary matrices. So now let's find the determinant of AB, because we just found the determinant of A. So we know that we have the string of elementary matrices times A equals I, and then we can multiply B on both sides to get that equation. Now we can break it up into the separate determinants by the elementary matrix lemma again, except determinant of AB has to stick together because we don't know that we can separate those yet. But now we can divide over the elementary matrices again, like we did back here. And we will get that determinant of AB equals 1 over the determinant of all the elementary matrices times determinant of B. And now we can substitute in A, because A was 1 over the determinant of all the elementary matrices. So now we get determinant of AB equals determinant of A, determinant of B by substitution. But we are not done yet. Now we need to assume that A doesn't row reduce to the multiplicative identity. So going that way, assume A doesn't row reduce to the multiplicative identity. That means that a string of elementary matrices times A, when A is going to be fully reduced, that will produce some matrix Z that is fully reduced that isn't the multiplicative identity. And we found earlier, not in this video, but earlier in the class, the linear algebra class, that if a matrix is fully row reduced and isn't the multiplicative identity, that it will have a row of all zeros. So we're going to be using that, so keep that in mind. So now we know, again, that we can split up these matrices with the determinant because they're elementary matrices. So determinant of the string of each elementary matrix times the determinant of A equals the determinant of Z by the multiplicative inverse theorem. And we know the determinant of Z equals 0 because the determinant of a matrix with a row of all zeros must be 0 by the way cofactor expansion works. If you don't believe me, you can go ahead and try it. But that's just the way that we've defined cofactor expansion. So therefore, the determinant of A must be 0 because the determinant of an arbitrary elementary matrix is non-zero. We proved that earlier in the video. We didn't prove it, but we gave support, and you can prove it if you so choose, but there just isn't time in this video. So, because the determinant of an arbitrary elementary matrix is non-zero. So, by the way that real numbers work, the determinant of A must be 0 because you can't have two non-zero things being multiplied together and getting a 0 for a solution. So determinant of A must be 0. Now let's find the determinant of AB. Well, we know the string of elementary matrices times A equals B, or equals Z, so we can multiply B on both sides. And again, we can separate each of these with the determinant by the elementary matrix lemma, but keeping A and B and Z and B together because we don't know we can separate those yet. And we know that the determinant of ZB equals 0 because a matrix times a matrix with a row of all zeros will result in a matrix with a row of all zeros, and the determinant of a matrix with a row of all zeros is 0. So the only new thing here is that if you have a matrix with a row of all zeros and you multiply it by any arbitrary matrix, that matrix will have a row of all zeros. Again, if you don't believe me, you can check that out on your own. So now, the determinant of AB equals 0 because the determinant of an arbitrary elementary matrix is non-zero. So, by the way that real numbers work, the determinant of A must be 0. Therefore, determinant of AB equals determinant of A, determinant of B, because both sides are going to be equal to 0. Because determinant of AB equals 0, and determinant of A equals 0, and anything times 0 is going to be 0. So 0 equals 0. So we have shown both cases, so now we are done. And that was the presentation of my introduction to matrices, the end. I hope you enjoyed.